All right, so now let's look at an example of how you could apply the Newton method for systems and nonlinear equations. So this is an application. Okay, so I'm looking at the unconstrained minimization of a function of several variables. Okay, so the problem is as follows, right? So I want to minimize some objective function which depends on x1 to xm. Okay, so you know that if you're looking at this minimization problem, it's like that what you want to do is you want to solve the system of equations to say that the partial derivative of this objective function with respect to each of the component variables vanishes. Okay, so f1, which depends on x1 to xm, right, it's just d phi dx1 of x equals to 0. So I get a system of equations associated with that minimization problem. So let's look at an example of this. Right, so let's say that I have a function of x and y, which is 3x squared plus 4, well, plus just y to the 4th power. Okay, so I want to write down the stationarity conditions. So d phi dx is equal to just 6x, and then d phi dy is equal to 4y cubed. Okay, so that's the system I want. f1 xy is this, f2 xy is that. So I can write down the Jacobian associated this, Jacobian which depends on x and y. It's df1 dx, df1 dy, df2 dx, df2 dy. Okay, f1 is 6x. Okay, so the partial respect to x of 6x is 6. Partial of 6x respect to y is 0. Okay, f2 is 4y cubed. Partial of 4y cubed respect to x is 0. The partial of 4y cubed respect to y is 12y squared. Okay, so that's my Jacobian. All right, and so my iterative scheme is saying that alpha n plus 1 is equal to alpha n minus okay, so 6, 0, 0, 12 y n squared inverse applied to f. So that's just 6xn and 4yn cubed. Okay, where alpha n is equal to x n y n. Okay, so that's basically the iteration. So for Newton's method, okay, so let's just say something about the convergence rate for this. All right, so you can observe that the solution, the minimizer, right, is just at the origin. So you can look at the Jacobian at that. It's going to be 6, 0, 0, 0. Right, so this is singular. So if you recall, if the Jacobian at the root is singular, then Newton's method converges only linearly. So Newton's method converges only linearly for this problem because the Jacobian it's like at the root is singular. Okay, so that's just an example of how you could look at a minimization problem. It's like for a function involving several variables, get a system of equations having to do with the stationarity. It's like of that function with respect to each of the variables. Now you have a system of equations, and then you can solve this, or you can approximate the solution to this using Newton's method by computing the associated Jacobian. Right. You can actually check that the Jacobian here is really the Hessian of the original function, right? So I should remark also that, right, J here is the Hessian of this objective function. Okay, so what I mean by that is that in this case, jxy is equal to this type of thing. Right? So yeah, so whenever you're doing minimization, it's like of a function, a scalar value function involving several variables. The Jacobian in the Newton method is going to be related to or actually the Hessian of that function. Okay. Anyhow, so let me just stop here for now.